Everyone, welcome to the channel. Today's topic is computer vision and artificial intelligence AI. In this video we'll cover what is computer vision, its applications, challenges and solutions. Then we'll deep dive into how machines process vision like humans, how computer vision works. Then we'll look into vision model techniques. In the first two slides, we'll focus on computer vision essentials. What is computer vision and what are its applications? Let's get started. Computer vision is a field of artificial intelligence AI. In computer vision, machines process visual information such as images, videos, and make decisions or predict output based on visual input. CV is the short form for computer vision. When we see a dog or a cat, a tree or a ball, we immediately recognize the animal's objects. This is because our brain processes the visual features of a dog like tail, legs, a tree with branches, fruits, leaves. Our eyes captures the images, brain processes the image information and identifies the objects. So how does computers capture the images? It is through camera. Computer captures the images or real-time visual data from camera. Then images are processed on computers or mobile devices using computer vision algorithms. In these four pictures, there are objects, birds, trees, sun, football. The images also have some signs and symbols indicating traffic light, which means ready to walk. The image also has some text on board with word open. Camera captures these images and computer vision artificial intelligence techniques not only identify the objects, trees, football, but also understands the text in the image, that is the word open, which indicates store is open. Computer vision algorithms and techniques also understand the meaning of symbols that traffic light indicates, that is, ready to walk or cross the road. Now let us look into the applications of computer vision in next slide. Computer vision is used in security systems for face recognition on mobile devices for unlocking your phone using face detection. In Google search bar, if you have noticed, there is a square box icon next to mic icon. The square box camera, when you hover over it, says search by image. Yes, you got it. That is Google Lens. The Google Lens uses computer vision to identify objects, text in images, and analyze the images. Computer vision is also used in manufacturing industry for detecting faulty products and automatically remove faulty products from production line. This improves the output quality of the product. In healthcare, detecting diseases through image analysis, computer vision is used in agriculture sector to capture the plant health and remotely monitor plant growth and crop yield. Computer vision also used in smart check-in and smart checkouts at airports and retail stores. Let us understand the power of computer vision with a use case. A customer ordered fruits and some products from online shopping store. After delivery, customer found that oranges are not fresh, rotten, spoiled, damaged. Customer want to return the oranges and claim refund from the online store. Then customer takes pictures or videos of damaged oranges and uploads the images and videos to the online store to return the fruits or refund or exchange with some other items. Once customer uploads the image to the online store, computer vision AI model detects whether the fruits are really damaged or the customer uploaded manipulated or fake images or distorted images of oranges in order to claim refund. Computer vision analyzes the uploaded images of fruits and accepts customer request to replace the fruits or rejects the customer request in case the uploaded images are fabricated or manipulated. Computer vision AI models can also identify well in advance whether the fruits are damaged during packing process and remove those items before packing. This automated process of identifying the damaged products and removing them from the packing increases the efficiency of the manufacturing industry. This also removes the burden of manual or in-person store visit of customer to exchange or return the products. This quick turnaround automated support system using computer vision AI models and machine learning algorithms improves customer satisfaction. What are the challenges in computer vision and what are the solutions to these challenges? First comes image quality. The input image data to the computer vision should be bright, pictures should be taken in good light condition. Dull and blur images will not have all the necessary details. Pictures taken from high altitude, in rain and other environments need pre-processing before feeding the image data to computer vision. CV has to understand the variations of the image like grayscale, that is black and white images, or color images RGB, red, green and blue. For scene understanding, frame by frame, RGB is better choice. Grayscale images are suitable for optical character recognition, that is OCR, which reads text from images. If the input images are of poor quality, then image pre-processing helps in improving the image's quality by resizing the image, removing blur, noise, and adding edges to objects. Then these improved images can be used for training computer vision AI models. Deepfakes identify and remove deepfakes and manipulated images from the training dataset to avoid bias and hallucination problems in the output. The next most important factor is data labeling. Label the image data accurately. Label dogs as dogs and cats as cats. If data is not labeled correctly, AI model fails. While collecting input data, avoid bias for better outcomes from computer vision models. Now let us deep dive into the technical details of computer vision. Machines learning vision. How machines understand the visual data. Let us understand the overall steps involved in machines processing the visual data and then we'll deep dive into each step. Computer vision AI models are trained with image input data. First step is cleaning and pre-processing image data so that clear images are input to the CV. Then break image into RGB pixel, grid or image tokens. Then embeddings, which are list of numbers that capture the essence of the image input. Next step is feature extraction and data labeling. Based on CV application, in some cases, entire image is labeled and in some cases, each object in the image is labeled. Then features of the objects are extracted from the images. This is called featureization. Features help machines to identify and classify the objects in the images. Features in the images are edges, corners, texture, shape of the object. Features can be handcrafted if the image data set is small. If image data set is large, then neural network called CNN, convolution neural network, is used so that model can automatically learn features from the data. CNNs are trained to look at images and convert visual information into single vectors or embeddings. The next step is train the model based on your objective. If you want to classify the images from large image dataset, then train the model with image classification algorithms. If you want to train the model to identify the objects in the images, then train the model with object detection algorithm. Similarly, image segmentation is used for applications of street scene for self-driving cars. Computer vision not only recognizes the labeled objects like cars, people, and traffic lights, but also understands their relationship within scene. We'll look into these algorithms in the next slide. Next step in the machine's processing visual data flow is model training and validate the output. The objects or the features extracted are compared with the already trained AI model which learned these patterns in visual data. Then evaluate the AI model for performance. Measure the metrics like accuracy, precision, recall, F1 score. These metrics are explained in detail in video titled Machine Learning Must Know Concepts Part 1 and Part 2. I have provided the link of those videos in this video description. Then comes model accuracy. Accuracy of all nines, that is 99.99% is considered good for any AI model. If desired accuracy is not achieved, then retrain the model. Then finally deploy the model for production. In the next slide, we'll look into each of these steps in detail. Let us start the slide with the first step, feature extraction. How machine learns the features of images or videos. Let's say image has a dog, a car, or a ball. Then how does computer vision identify these objects in the image? Computers recognize these objects by detecting unique features of each object, that is edges, corners, textures. What are edges? Edges are boundaries between the objects. If the object is cube, then there are 12 edges. If the object is a circle, then 1 edge. Corners are points where two edges meet. For cube, 8 corners, and for circle, 0 corners. So fruits like apple in an image has edges but no corners or vertex, as the fruit is almost circle in shape. Objects like car in an image has both edges, boundaries, and corners, vertex. Then comes shape analysis. Analyzing outline of images. Apple and oranges. Textures are patterns of pixel intensities like smooth texture, irregular texture. Let us take a quick look at image dataset. For small image dataset, handcraft features, edges, corners using machine learning algorithms like KNN for classification. For large dataset, use deep learning algorithms like CNN to extract features automatically. How CNN works? CNN extracts image features, edges, textures. Then CNN has a pooling layer which retains important information of image, and then CNN has connect layers for output, that is image classification. For more technical details on how CNN works, please watch my video on deep learning and neural networks. I have provided the link for that video in this video description. For complex dataset, use transformers as they work on attention mechanism. Consider an image scene which has both text and objects. How does machine see, read, and understand the context of image or understand scene? Here comes the transformer architecture and clip algorithms. The model divides the image into smaller patches or smaller grids, RGB pixels. These smaller patches are converted into image tokens or numerical vectors. Transformer architecture considers the entire image when generating feature representations. Transformer process text and objects as a sequence and understand the context. As we are now ready with the data, we'll start training the AI model for computer vision applications. Moving on to the next slide, let us look into the vision model techniques for image classification, object detection, and image segmentation. Image classifications tells us what is in an image. As we saw in previous slide for image classification, deep learning and neural network based model techniques CNNs are used. In this, dataset is trained with CNN, model learns features and predicts new images. For example, an image or a video with traffic on road is fed to image classification model. Then the model classifies the objects car, truck, pedestrian, traffic lights, buildings. Next comes object detection and tracking. This tells us what objects are present in the image and where those objects are located. Input image, or in case of video, frame by frame data is fed to the object detection algorithm like YOLO. You only look once. These algorithms predict the bounding boxes and labels and also identify the object movement. This gives the coordinates of the object. In the image, what are the coordinates? X coordinate, Y coordinate of objects, car, truck, and also track the movement of car in video frame by frame. Next comes image segmentation. Images are made of pixels. Image segmentation classifies every pixel into category by positioning image into meaningful regions by using features like color edges. Images are fed to the segmentation algorithms like RCNN, then pixels are classified. In image, car pixels belong to car, truck pixels belong to truck. Let's say if there are more cars in the picture, then each car is labeled separately like car 1 pixels, car 2 pixels, and accordingly the pixels for each car are categorized. In autonomous vehicles, which are completely driven by AI, that is self-driving cars, identify vehicles, pedestrians on road, roadblocks, traffic jam, etc. This data is captured in real time and fed to the self-driving car control systems so that the self-driving cars can make decisions in real time for safe navigation. Moving to the next slide. Next slide is on advanced computer vision techniques, vision transformer models. ViTs transform image into sequence of tokens which enables them to capture global context of image such as scene understanding. Transformers can capture relationships between distant parts of an image. Let us look into the building blocks of vision transformer models, ViTs. First step is to get the image data such as MNeST image data set. Divide the image into patches. If the image size is say 256 by 256, then divide this image into 8 by 8 or 16 by 16 pixels. If the image has a car, then these patches help in focusing on car wheels, windows, etc. Patches of an image have spatial positions like top left, bottom right. The spatial positions gives meaning to the image structure. Pass these patches through embedding layers, add positional encoding so that each patch embeddings understand the position of each patch in the original image. Without positional encoding, the self-attention mechanism treats each patch as independent of others, resulting in a loss of structural information. Then pass these patches into transformer attention mechanism to find the relationship between the patches and understand the local and global context. Input images has objects like car, traffic lights, bus, so that context here is street scene. Next slide. Compare vision model techniques. CNN uses pooling layer to retain important information and remove noise, suitable for large data set with simple parameters. CNNs are good at identifying local patterns, that is close object in image close pixels. They consume less memory. VITs, visual transformers, divide the image into patches and then process using positional encoding and attention mechanism. We already saw this in the previous slide. VITs are suitable for understanding global context of distant pixels within an image. Transformers does parallel processing, so they are fast, but they are computationally expensive. YOLO, you only look once. This technique identify and localize the images in one go. For high resolution images, less computations compared to visual transformer models, YOLO can be used. Next, CLIP. Advanced computer vision techniques for multi-models. In multi-models, computer vision can look at an image and answer questions about the image. Contrastive language image preprocessing CLIP integrates language and vision for unlocking multimodal capabilities. Multimodal aligns image and text. Use CNN for images and transformer techniques for text. VQA, Visual Question and Answer. What is this VQA system? This system takes image and text as input and provide answers. For example, if you ask, what is the color of the car in the image? Or what is the color of the truck in the image? The multimodal system using CLIP processes the image and reply that the car in the image is white, or it's a black car, or it's a red truck. Very interesting concept. Now let us move to the next slide. This slide is interesting. A quick recap. Regarding VIT, that is visual transformers, which of this is true? Positional encoding, bag of specials, attention mechanism, all the above. Bag of specials is used in YOLO. So positional encoding and attention mechanism are true about VIT. So answer is A and C. Next question. Which of these vision model techniques best suitable for multimodal? Vision transformers, you only look once, CLIP, none of the above. Vision transformers are good for global context. You only look once is suitable for object detection and tracking. CLIP is best suitable for multimodal, that is text and image. So answer is C. If you have any questions, please let me know. This brings us to the end of this video. Please like, share and subscribe to the channel. Thank you for watching. See you in the next video. Until then, happy learning.